The simplified version of Newton's third law states for every action there is equal and opposite reaction. So a common confusion from this is, why do things still move? Well, I think the common example that I should use here is the box example. So let's say the box has a mass of 5 kilograms, and this is you who's trying to push the box, or who's trying to give the box a force to the right here. Now I'm gonna ask you to draw the free body diagram, or FBD, of the box. Well, here is the box, a dot, and here is the force that it feels, which is applied by you. We're going to ignore frictions in this case, so the confusion starts from here. Most people think for every action there is an equal and opposite reaction means this. Here's the FBD of the box, right? So they think this is what the box feels. But no, that's not what Newton meant. You need to remember this. You cannot exert a force on itself. So this is wrong. Okay, so this is wrong. What Newton really meant is the equal and opposite force that a box exerts back is, wrong color, is on you. So here's the FBD of you. This is what Newton meant. So the box will oppose a force on you. So that's why earlier I said it's very important to understand that you can't exert a force on itself. Okay, so you feel a force in the opposite direction that is equal. So, so where do we go from this? Well, let's do some calculations, simple calculations. Usually in a physics problem, they will give you the force. So let's say the force is 5 newtons, and I'm going to connect Newton's third law with Newton's second law. So Newton's second law, in simplified version, states the net force equals to ma. Let's plug it in and see what happens. So if the force is 5 newtons, right? This is the net force. Remember, we're ignoring friction here. This is the net force. This is the only force that's present on the box. And the mass of the box is 5 kilograms. So you calculate A, and A equals to 1 meters per second squared. Now, let's say you are much heavier than the box. Let's say you are 50 kilograms, okay? And using Newton's second law, you will get an acceleration of 0.1 meters per second squared. So you notice here, this is the acceleration of the box, and this is the equal and opposite acceleration of you. You notice that since the box has less mass, it accelerates more. Matter of fact, it actually has 10 times the acceleration than you. So why in real life you don't move? Let's say the box is on a table here. And how come you don't move but the box moves? Well, remember earlier we're ignoring friction? There is friction. So when we add in friction, here is friction, F sub F. So this is why the box moves when you push it. The force that you exert on the box must exceed the force of friction. Notice how this arrow is longer than this arrow. So the magnitude of the force that you apply on the box is much greater than the friction, which is why the box moves. Now, when you push a box, you're standing on ground here, right? You're standing on the ground. You don't move. But actually, Newton's third law tells you that yes, the box does give you a push, give you a force. So what I'm trying to get at is, yeah, when you're pushing a box on a table, you do not move, but that doesn't mean there's no force on you. The box, the equal and opposite reaction force by the box, it's still there. It's still here. The reason why you don't move is because of your foot and the ground, right? The friction force this way. is opposing this equal and opposite force exerted by the box, quoting Newton's third law. Okay, so now that hopefully your confusion has been resolved, I'm going to move on to one last example, just to help you understand it further. So imagine here is space, and you're here in space at rest, okay? And you have a hammer in hand, and your goal is to move to the left, this way. What would you do to move to the left? So first of all, space has negligible friction. And if your goal is to move to the left, I hope you think about Newton's third law. So if your goal is to the left, is to move to the left, by Newton's third law, you have to apply a force to the right in order for you to move to the left. So that's an easy thing to do because you have a hammer in hand. So what you can do is you exert a force on the hammer to the right. Here's the FBD of the hammer. It will be this way. So how you can do that is you just throw it using all your muscles, using everything that you can, right? To throw it to the right. And guess what? By Newton's third law, since there is no friction, remember, here is the FBD on you. Notice how I'm drawing separate FBDs. So you will feel an equal and opposite force to the left.